Okay, here's the Zoom meeting for Physics 231C, February 9th. So after the first exam, and we're beginning to study now Chapter 5, which is entitled Work and Energy. Everybody knows that energy is important, but what is it? How many people can say exactly what is energy? Most students in this class are science majors, and no matter what science you're interested in, you'll be dealing with energy. But energy starts in physics. And it's related to force through the concept of work. Work is, in physics, a kind of energy transfer. There's another kind of energy transfer called heat, and we'll study that later in the semester. So you need to read chapter 5, take notes, and write the most important equations in your notebook. So, for example, you should be able to answer these questions. What is work? In everyday life, work means some kind of useful task. But in physics, work is defined in a more mathematical way, a more technical way. Work is force multiplied by distance. So here's the equation for the case where the force depends on position. Now, that's related to kinetic energy. And what's kinetic energy? Well, kinetic energy is very simple. It's the energy of motion. And it's just given by an equation. Kinetic energy means 1/2 the mass times the speed squared. That's the amount of kinetic energy that belongs to a mass m moving with a speed v. It has energy 1/2 mv squared. Now, there's another kind of energy. Well, actually, there are several other kinds of energy. But for chapter 5, the other kind of energy we'll be considering is potential energy. Potential energy is a little more subtle than kinetic energy. Kinetic energy is just an equation. Potential energy, first of all, not all forces have a corresponding potential energy. The forces that do have a corresponding potential energy are called conservative forces. So, for example, gravity, spring, those are conservative forces, and there are potential energies for those forces. What's an example of a force which is not conservative? Well, friction. Friction is not a conservative force. The definition of the potential energy for a conservative force is if the object on which the force is acting is displaced by a displacement delta x, then the potential energy changes by negative F dot delta x. It's, again, force times distance. But in this case, force times distance gives you the change in a function, or rather the negative of the change in the potential energy function. Now, one thing we're going to find in chapter 5 is that you can use the concept of conservation of energy to solve a lot of physics problems. In a system where there are only conservative forces, the combination of kinetic energy and potential energy is constant. No matter how the system moves, no matter how the kinetic energy changes and how the position changes, no matter what changes occur, the total energy will not change. And that's a conservation law. So you can use that to solve some physics problems, because 1/2 mv1 squared plus u of x1 must be the same as 1/2 mv2 squared plus u of x2. And so this gives you an equation you can use to relate speeds and positions. Now this is for physics, it's for mechanics really. But conservation of energy goes way beyond mechanics. Conservation of energy is a universal principle, and it's used in all branches of science or engineering. So these are the equations you need in your notebook, because these are what you're going to use to do the homework problems. Now let's go over a few homework problems. This is a problem from the book. It's 5-94. It involves a roller coaster. So you have a roller coaster car, which is going to coast down a hill and then go into a loop-the-loop. And we'll have various parameters. So we always start by drawing a picture with labels. So here's the picture of the track and the car. It starts up here. We'll label the height h as the initial position. It rolls down the track. Then it's moving very fast at the bottom. Now it'll go on to the loop-the-loop. And the loop-the-loop will label a radius of the loop-the-loop. When it reaches the top of the loop-the-loop, it's very important that it not fall off. That will depend on the speed. So let's label the speed v2 at the top of the loop-the-loop. Let's label v0 as the speed at the top, which might be 0, but might not be 0. And let's label the speed v1 as the speed at the bottom. So there's the picture labeled with various parameters which are necessary to solve the problem. Now, we're going to solve this problem not using forces. We won't analyze forces and accelerations. We could analyze forces and accelerations. In fact, we could solve this problem by analyzing the forces and accelerations. You know, we've studied forces, we've studied accelerations. There's a gravitational force. There's a contact force between the roller coaster car and the track. There's acceleration due to gravity on a slope. We've studied that before. There's motion on a circle. So we've studied circular motion before. We know there's going to be an acceleration on the circle. So we could analyze this problem by considering forces and accelerations, and it would be very difficult. But we can solve this problem much more easily by using the concept of conservation of energy. So step one is to draw the picture, and we got the picture. Step two is to write the relevant equations. So we're going to use conservation of energy. If the car starts at the top with no speed, then the energy it has at the top is the energy due to gravity. That's mgh, a kind of potential energy. But the energy it has at the bottom will be only kinetic energy. It's moving very fast at the bottom, but it's at the ground level, so it no longer has any kinetic energy, any potential energy. So the energy at the bottom is 1/2 mv squared. This isn't showing up quite right. It should be 1/2 mv1 squared. at the bottom. So it has 1/2 mv1 squared. That's the energy at the bottom. mgh, that's the energy at the top. Those have to be equal. Now it goes onto the circle. And again, energy is conserved. So the energy here at this part of the circle is 1/2 mv1 squared. But at the top of the circle, the energy is 1/2 mv2 squared. 2 means at the top of the circle. So this is 0.1, this is 0.2. Plus the potential energy, which is mg times the height. The height here is 2 times the radius. So we have 1/2 mv1 squared is 1/2 mv2 squared plus mg times 2r. So that gives me 2 equations that I get from conservation of energy. Now I need one more equation because I need to find out what's the condition that the car will not fall off the track here. And that comes from analyzing a force. The mass times the acceleration, so that's mv2 squared divided by r. That's the centripetal force. That'll be a combination of gravity pulling it down with a force mg and a contact force because it's still in contact with the track, which will be some positive contact force. So I can say it's enough to say mv2 squared over r is greater than mg. That ensures that it's in contact with the track here. So that gives me 3 equations. And it depends on what the question is. I don't know what the question is. There are actually 2 questions. But whatever it's asking for, you can use algebra to analyze these equations and get the quantity that's being asked for. It's probably asked, what's V1? One of the questions is probably, what's V1? Well, I can directly solve that from this equation. M's cancel. It'll be 2GH times the square root of 2GH will be V1. The other question is probably, how high should H be so that it'll be in contact with the track at this point? It has to be moving fast enough that the force of the track is holding it, pushing it towards the center of the circle. So that's for calculating H. Well, you know, I have this inequality. So by analyzing this inequality, this would have to be V2 squared. V2 depends on H, or depends on R by this equation. So, you know, I'd have to put these 3 equations together and use algebra to get the answer to what's the value of H that it needs. Oops, what happened to my picture? I lost the picture. All right, so that's the typical method for solving any problem. And you saw how we made use of conservation of energy. I wonder if I can get this back by starting this over again. Nope, it's lost. Well, all right, let's go on to another problem. This is again a problem from the book. It has to do with a pendulum. So we draw a picture of a pendulum. Here's a pendulum, has a mass m on a string with length L. It's swinging back and forth. I can define an angle theta, which is the angle of the string relative to the vertical. So here's the picture. I label various quantities. I don't label the quantities by their values. I just label the quantities by their variable names, L, M, and theta. Now in this problem, I'm going to have some initial angle. Let's say it's here. I'm going to let go of it at this point and let it swing back and forth. Then from that point on, it'll just swing back and forth. So I'll have an initial angle. I'll have potential energy related to the height of the ball. So I'll have to relate the height of the ball. Let's call that coordinate y. I can relate y and theta. So here's a little analysis. Y is the distance from the bottom here up to the height of the ball. This length is L. This length is also L. This distance would be L cosine theta by trigonometry. So this distance, the height, would be L minus L cosine theta. So that's another equation I'll want to use. And I can relate the speed of the ball as the ball is swinging back and forth. It has some speed directed towards the tangent to the circle. I could solve this problem using forces and accelerations. There would be the acceleration due to gravity and the string tension. So there'd be two forces. There'd be a centripetal force, which would be the tension in the string. That will give me the centripetal force. There'll be a centripetal acceleration, which is v squared over r. R is the radius of the circle, so that's L. So you see, I could analyze the whole thing, uses forces and accelerations, but it's easier to use energies because energy is conserved. The only force here, well, there are two forces here. Gravity, that's a conservative force. And the string tension is a kind of elastic force in a way. It's a conservative force as well, but it's not really so much that it's conservative, but it's doing no work because there's no displacement in the direction of the string. It accelerates in the direction of the string, yes, that's a centripetal acceleration, but it's not displaced in the direction of the string because the string always has the same length L. It's moving on a circle. But it's much easier to just use conservation of energy, which is one simple equation, which says the energy, when it's at the initial point, is mg times y for that point. And y is L minus L cosine theta. So this is the initial energy when it's up here. It swings down at the bottom, it has no potential energy. All of that potential energy has been converted into kinetic energy. And the kinetic energy is just 1/2 mv squared. Kinetic energy is always very easy to write down. So I don't know what the question is in this problem. Oh, you're supposed to give a general response, and then you're supposed to give a numerical response. The length of this. Oh, you're supposed to calculate the speed at the bottom. So you're supposed to solve for v. Well, it's just that one single equation. Not too much algebra involved. It's just this one equation. M's will cancel. So it doesn't depend on how heavy the bob of the pendulum is. V will just be 2GL 1 minus cosine theta, the initial theta, take the square root. Here's another example. A diver dives from a platform. At a height psi above the water, her speed is phi. What's her kinetic energy as she reaches the water? So we start by drawing a picture. So here's a picture of the platform board, the diving board. Here's a picture of the diver. She comes off the platform and undergoes free fall. Now, we studied free fall in chapter 2. So we could solve this problem by using free fall. You know, the equations for constant acceleration. Now, the answer we want is kinetic energy. So just solving the free fall problem won't answer the question. But then we could go and calculate the kinetic energy after solving the problem of free fall. But it's going to be easier if we just use conservation of energy, because the only force in this problem is the force of gravity, and that's conservative. So the easy way to do this problem is to just use conservation of energy. Now, I draw the picture here because we're using non-traditional symbols for the variables in the problem. Psi is a height. Its initial height is 6.3 meters. Phi is a speed, so its unit is meters per second. So it'll help me to do the problem if I have a picture which shows me the meaning of psi and phi. Now, step 2 is to write the equations. Well, energy is conserved. So the kinetic energy, 1/2 m speed squared, which is in this case phi squared, 1/2 m phi squared, plus mg times the height, that's the potential energy of gravity, is constant. So 1/2 m v1 squared plus mgy2 psi1 is, well, let's just call it K2, since that's the unknown in the problem, plus mg psi2. So those are the equations, just the equations of conservation of energy. It's really the same equation. And now we just apply a little bit of algebra, then we can start doing the calculation. So what's the unknown, K2? What's phi1? Well, phi1 means the speed at the board, meaning the vertical speed. But that's 0. I'll define 1, in my picture here, I'll define 1 as the position at the top of the board and 2 as the position in the water. So phi1 is 0. Psi1 is the initial height. Psi2 is 0. So that's when it's entering the water. The water is down here at ground level. So this term is 0, this term is 0. Try to calculate K2, it's just mg psi1. So in fact, I didn't even really need these equations. I could just say this problem is solved by conservation of energy. The potential energy at the top is equal to the kinetic energy at the bottom. That's because the total energy is equal at both places. But at the top, the only energy is the potential energy. And at the bottom, the only energy is the kinetic energy. So even without writing out any equations, I could just say K2 is mg psi2 minus psi1. Now, if there is some speed at the top, I could add the kinetic energy 1/2 m phi1 squared. In this problem, phi1, okay, so she has an initial speed at the top. So I guess she jumps up and then she starts coming down. So when she's at height 1, she is moving down a little bit. That is given. And now you pick up your calculator. So you know all the values. We have to know M, we have to know phi 1. We have to know M, that's given here. Psi, we know psi. Psi 2 is 0, so that's actually not there. So it's just that the kinetic energy at the bottom is equal to the kinetic plus potential energy at the top. Here's another example. Throw a baseball horizontally. The parameters of the throw are height h and speed s. With what speed will the baseball hit the ground? And use concepts of energy to find the answer in one step. So we could solve this problem. So we could solve this problem using projectile motion, which we studied back in a previous chapter. We could analyze the motion of the baseball as a projectile. Here's the picture. There are two given quantities, the height at which the ball is released and the speed when it's released. And now I could calculate how fast it's moving when it hits the ground. That's the question. What's the speed when it hits the ground? And I could just solve it as a projectile problem. But that would be several steps to get the answer. If I use concepts of energy, I can get it in one step. The energy when the ball is released by the pitcher is 1/2 ms squared plus mgh. The energy when it hits the ground is 1/2 mv final squared, where v final is the speed of the ball when it hits the ground, and no potential energy because ground is ground level. The unknown is Vf. We just have to solve this equation, multiply by 2 over m, take the square root. So it's s squared plus 2gh. Done. One step. Whereas if I had to analyze this problem using projectile motion, I'd have to use various equations to get the answer. So energy simplifies the analysis of a lot of problems. Did that one, did that one. Here's a problem where energy is not conserved. But we can use conservation of energy to learn something. We can calculate the heat. Total energy is always conserved. There are two ways that energy can be transferred from one part of a system to another. One is by work, one is by heat. Now, the theory with heat is called thermodynamics, but this is a simple problem. The figure illustrates a long slide. A child starts at the top at a height h1, have potential energy mg h1. Slides down at a height h2, the speed is v2. It'll have a lower potential energy, mg h2, and the rest will be kinetic energy, 1/2 mv2 squared. And now, how much energy has been transferred to the surroundings in the form of heat and air currents? As he slides down the slide, there's friction. And so his pants are getting a little warm. There's some transfer of heat in the form of atomic energies from sliding down from the friction. And also, as he goes down through the air, he's stirring up the air. So there's a kind of, consider that a kind of heat, because he's stirring up the air. He's sort of adding energy to the air, is raising the temperature of the air by a little bit. Even aside from the heat, he's doing work on the air, so he's setting the air into motion. But I can't see what motion is given to the air because air is transparent. I can't see it. So the question is, how much energy was transferred to the surroundings? We call that heat. We use the symbol Q for heat. So what we're trying to calculate is this heat, Q. The initial energy at this point, let's call that E1. The child's energy, the mechanical energy at this height, we'll call that E2. And any difference is a transfer of energy by heat. So to E2, we add Q. Because total energy is conserved. Q is the amount of heat. It's the amount of energy transferred to the surroundings, to the frictional slide or to the air that he's passing through. So I can write equations for E1 and E2. Then I want to calculate Q. So E1 will be mgh2, E2 will be E1 will be mgh1, E2 will be mgh2 minus a half mv2 squared, or plus a half mv2 squared. But I take E1 minus E2. And I've assumed that there's some observational method of determining how fast he's moving at this point. So we know V2. So everything on the right-hand side is a known quantity. Now we just start calculating the values with a calculator. And as usual, there'll be a unit. The unit will be the same as mass times acceleration times height. Mass times acceleration times height. Or mass times velocity squared. So the unit is going to be, let's figure out what the unit is in this problem. So what's the unit going to be? It's very easy to get the number, just use your calculator. But what's the unit? Your calculator won't tell you the unit. Well, from this, the unit would be kilograms. G has units meters per second squared. And H is a height, so that has units of M. Or I could use this formula. And the unit would be kilograms, that's M, meters per second. That's velocity squared. Of course, if I add quantities, they have to have the same units. And indeed, these do have the same units. So let's see, what's the unit? Kilogram meters squared divided by seconds squared. Now that's such an important unit that we give it a special name. That's called the joule, named for James Joule, who back in the 19th century developed the concepts of energy and energy conservation. So J, capital J, is the abbreviation for the joule. You see how if you keep the units when you do the calculation, you'll always get the unit of the answer. So you should never have to ask, what's the unit of the answer? It just comes out of the formula. Now, you have to know that kilogram meter squared per second squared is called a joule. That's what Lon Kappa will be looking for. All right. Let's look at, I guess it's one more problem. The figure illustrates a ski jump. Assume the top is horizontal. No, I mean that the top, I mean here is horizontal. Assume that it's really the bottom of the jump, but it's the top of the jump. It's the bottom of the ski jump, but it's the top of the motion through the air. Assume it's horizontal at this point. Assume the surface is frictionless. You're given the initial height. No, you're not given the initial height. That's the unknown. You're supposed to determine the initial height. You're given this height. You're given the height of the point where the skier leaves the ski jump. So that's the height of the bottom of the ski jump. We're trying to calculate the height of the top of the ski jump. And given D, that's how far he went through the air when he landed on the, hopefully a hill here. So hopefully he lands here on a hill of ice, and he continues on down. So yeah, correction. The launch point is horizontal. Now, we could treat him as a projectile, and we could solve this problem just using the equations of projectile motion. But again, it would actually be very similar to the previous problem, but it would be a number of steps to take that analysis of the projectile and convert it into the unknown H, capital H. But it's very easy to solve this problem using conservation of energy. So let's label the picture. We always draw a picture. Well, we already have a picture, but we should draw your own picture because you can get a better picture. At this point, we'll say the speed is V1. How big is V1? Well, by conservation of energy, mgh, that potential energy, is equal to mgh, this potential energy, plus 1/2 mv1 squared. The total energy at this point, which is partly potential energy, partly kinetic energy, that's equal to the total energy at this point. He starts out up here with, let's say, speed 0. So he just has potential energy, mgh. Now, through the air, he's following a parabola. So the distance traveled is v1t. I'm actually using a little bit of projectile motion analysis here for the dotted curve. The distance will be v1t. The height will be 1/2 gt squared. Just thinking about projectile motion. So I'm trying to calculate h. So how would I calculate h? Well, h divided through by mg. H is h plus, the m's all cancel. 2 v1 squared over g, and v1 is d over t. So that's d over t squared, and t is the square root of 2h over g. So here's the algebra. I mean, this is actually, I've done several steps of algebra in one equation, but you can see where it comes from. You know, from this equation, I get h plus v1 squared over 2g, h plus something over 2g. Here's V1 squared. V1 is d over t. It's d over, now what's t? T is the square root of 2g over h. And again, we can always check the units. The unit of height should be meters. And here's meters. So that's okay. What about this term? Well, this is 1 over acceleration. So that's meters per second squared in the denominator. So that's second squared divided by meters, where second squared is in the numerator. Here's d in the numerator, but it gets squared, so that's meters squared. And this is t. So it'll be divided by t squared. And now you see the second squares cancel the second squares. I have here meters squared, but divided by meters, so that's meters. So indeed, these two terms can be added together. They're both meters, and so I get h in meters. All right, I think I have one more. We've almost used 45 minutes, so I should quit pretty soon. Here's another problem. Consider a car on a horizontal road. When the car speed is V1, the power supplied to the motion by the engine is P1. So the engine is supplying a power P1. Where does that come from? Well, that comes from burning the gasoline. Well, we're not going to think about the gasoline. We're just going to say that there's a power P1 supplied to the car to keep it moving at a constant speed. You know, if there were no forces on the car, the power needed to keep it moving at a constant speed would be zero. That's Newton's first law of motion. Newton's first law of motion says a particle in motion remains in motion with the constant speed, unless there are forces acting on it. Well, there are forces acting on the car. There are frictional forces. The car, as it goes through the air, stirs up the air and sets the air into motion. Also, there's a kind of a friction between the wheels of the car, or the tires, and the roadway. So the wheel of the car is constantly being squished a little bit, expanding and contracting a little bit. So that'll convert into a frictional force. Heat. The wheels or the tires on a car are hotter if it's driving along a road than if it's just sitting there, not moving. So now, of course, friction is not a conservative force. So the forces acting on this car are going to reduce its energy, and we have to replenish that energy by supplying energy from the engine. That's why you have to have an engine to keep your car moving. So it says the additional power, that's the power supplied by the engine, makes up for air resistance and friction. And the question is, calculate the acceleration of the car. I guess it means this is the power that's needed to accelerate the car. So this is the power that's needed to accelerate the car. I wasn't quite reading that question right. This power goes into keeping the car, speeding up the car. Its speed is V1, but it's speeding up a little bit because you pushed on the accelerator. So it's at a speed V1, you push on the accelerator, now it'll accelerate. Because the engine will supply power necessary for the acceleration. Actually, the engine has to supply a little more than that to make up for air resistance and friction, but we're not going to analyze that. We're just going to analyze speeding up the car. So at a speed V1, you're supplying power P1. What's the change in its acceleration? No, what's the acceleration that it has? What's the change in its velocity? So we always draw a picture. So here's a picture. The car on a road, it's moving along with a velocity v1. It has a mass m. I hope it told me the mass of the car. Yeah, it's 910 kilograms. Now, the information I've given is called power. So I have to know what's power. Power is the amount of work done per unit time. That's the definition of power. In fact, in chapter 5, there's a whole section called power. And, you should have written in your notebook from reading the chapter, power is work divided by time. The unit of work is the same as the unit of energy, because work is a transfer of energy. So the unit of work is joule. The unit of time is a second. And joule per second is given a special name. A joule per second is a watt, abbreviated by W. So that's the unit of the quantity P. How are we going to use that to answer the question? The question is, what's the acceleration? Well, let's see. Work is force times distance. So that can go up here. So we draw a picture, we write down the necessary equations. One equation is the definition of power. The other equation is the definition of work. Now, acceleration is force divided by mass. So I can replace the force by mass times the acceleration. So the force, well, if I just put these two together, I see I have F delta X over delta T. Delta X over delta T is the speed. So that's F times V. And now by Newton's third law, F equals ma times V. And the problem is to calculate A. P is given, M is given, V is given. I just have to calculate A. But you see that, although that's a very easy calculation, it comes from several equations. The meaning of power, the meaning of work, and then Newton's third law, Newton's second law. Okay, so I've completed all the problems that I had prepared, so now I can stop the recording.